Good evening, everyone. Just want to check if I'm audible.
Good evening.
Good evening.
Good evening.
Perfect. Thank you. Good evening. Uh, I guess we still have a minute, and other participants are still running late as usual. So we'll get started in a minute. Like I guess it's already time. We can start. So we'll do a quick recap of just the test, what we worked out yesterday, and then we'll get started with today's topics. I'm sure like everyone would have received the email about the extension of couple of days that we have. So yes, we will ensure that like whatever is left out, we can cover up in next 2 days. Uh, yep. So moving back to yesterday's topic, primarily on the statistical testing part of it. So basically, we discussed about the hypothesis test. So what should be the right process or the steps we should follow? So once the data is collected, and we have to start with the testing. So what should we do first? That should be always checking normality. So if you know the data is normal or non-normal, basis which you will know which side of the test would you be going with, a normal side of the test, which is parametric tests. These are also known as parametric tests. So parametric is all about normal test, and uh, non-parametric are the non-normal ones. So this is non-parametric. So either you will be doing a parametric or non-parametric test. It will depend on the normality test. If you figure out the data is normal, that we will be comparing the averages in the data set. If the data turns out it's non-normal, then you will be comparing the medians in that case. So if, once the data is normal, the next thing we would definitely want to check it out if the data is random or not, because for ANOVA, we need the data random. And if we have already checked the randomness, then pretty much we have a clear line of sight whether we will be doing ANOVA or we will be doing a Kruskal Wallis going forward. So normality, when tested, we always go, and if it is normal, then we always check randomness well in advance. So we have a very clear line of sight whether are we going to be doing ANOVA at all or not. So say we tested the data is normal, data is random also. So pretty much within the data set, we will have some excess will be numerical, some excess will be categorical excess. So for numerical excess, we always use correlation with scatter plot, which will be standard always. And when there is a categorical X, and if the data is normal and random, so pretty much that's what we're going with. For two groups, we always use a two sample t-test, comparing the averages of two groups. And if it is more than two groups, then pretty much we end up using a one-way ANOVA. In case the data would have been non-random, then we would have used a Kruskal-Wallis or a Moore's median test instead of that. But not only this criteria, there is another criteria which we must qualify. So ANOVA is a sensitive test and the most sensitive test actually. So yes, we must qualify three conditions for ANOVA. The data must be normal. We must have already checked. Otherwise, we won't have been talking about this. The data must be random. Yeah, we would have done already that prerequisite test. And the variance between the groups must be equal. So we would be doing a test for equal variance, and that will help us understand if the data, the groups being compared in this ANOVA, are they have like do they have an equal variance or not? And if it is equal variance, then pretty much we are good to go ahead and perform the ANOVA test. In case the variance is not equal, then we don't have a choice. We have to go with Kruskal Wallis or Moore's median in that case. So that was more about the normal data. When we talk about your management might have given you a target to improve the average of the process and stuff like that. That's when averages, generally we talk about averages. Weird case scenario that we talked about, yes, your management could be somebody who's a very like who is statistically sound and might want to give you a target which is based on standard deviation or variance. We would like to reduce the variation in the process, and that's how the language of your project would be. The project would be like our process has say whatever 10 point something whatever standard deviation, and we would like to reduce this variation with from 10.5 to say 2.35 standard deviation. The reduction in variation in the process. Then pretty much the logic will still remain the same. Data is normal, numerical access don't get impacted. For two groups, we use a two variance test, or you can use a test for equal variance. Anything will work. For 2 plus group, you'll use a test for equal variance. So technically, you can just use a test for equal variance will take care of it. So if the data is based on the standard deviations, you'll have only couple of tests. Either you do a correlation or you do a test for equal variance. So you find out, are the groups having a significantly different variance between them or not? That's what we want to find it out. And then when the objective in here, in these tests is just to find out, do we have a root cause or not? That's it. There are a lot of x's. We would like to test those x's and find out if there is a root cause. Had the data been non-normal, then we would have performed almost similar stuff. But yes, correlation scatter plot will remain as it is. Numerical access doesn't change. For categorical X, yes, instead of two sample T, we will be doing a Mann-Whitney test. And for 2 plus group, we'll be using a Kruskal-Wallis or Moore's median. So it doesn't change at all when we talk about these uh, like testing and stuff. So if you want to sort of quickly like make a snapshot of this, like a easy, easy snapshot, like we kind of made a tree out of it. But if you just want to make a very, very simple stuff now, because we have the tree, like say if you're comparing, say this is comparing two groups and 2 plus groups. If you're comparing mean, you're comparing median, you're comparing variance or standard deviation, whatever you call this. That sort of is simplest way you can look at this entire stuff. Like, so whatever tree we have created, but that's more of the first stage. We should always form a tree. We know the flow chart sort of thing, but now because you're clear about it, well, when you're comparing averages of two groups, it's two sample T. When you're comparing averages of 2 plus group, we will have one way ANOVA. When we are comparing average of two medians of two groups, we use Mann-Whitney. For more than two, it's Kruskal-Wallis or Moore's median. For two groups variance, we use two variance or test for equal variance. And this one is test for equal variance in inches. Well, that having said that, but then you need to have those. You need to remember those conditions that we had for everything. Like so, those conditions needs to be remembered because herein it doesn't talk about those conditions. So conditions, yes, you have to still remember that. What will be the fail? When would you be using? Like in case of the ANOVA, what are the conditions and stuff like that. Yeah, that you have to kind of remember. So maybe probably you want to just type in these ANOVA conditions wherever it is. That should be sufficient for you to kind of a summarized version of all these tests that we have talked about. Okay, give me one quick second here. Get for ANOVA. These are the prerequisite conditions. I'll scroll down. Okay. And bottom line, there's only one thing which is left here. If you have a numerical X and a numerical Y, the only test we have is correlation plus scatter plot. That's a summary of what we discussed. And this is like technically, honestly, you would, when you kind of be doing a project, 99% of the project, you will end up doing these tests only. That's all what you will be dealing with. You either going to be comparing the averages of the groups, you might be comparing the medians of the group. Worst case scenario, you're going to be looking into this section, like the variance based testing. But yeah, when you're going to check ANOVA, you will be checking the equal variance also. So that those exceptions we already know. But these will be the most common test, unless until you fall into the other segment, which is not so common in projects. But yes, we cannot deny. But I said like 99% of the projects will be like revolving around this. So this is what we discussed yesterday. We'll continue with the another. So we have three types of Y business problem. A numerical X can be categorized as a normal X, normal Y, or a non-normal. So we have kind of covered the normal, non-normal here. What if you have a categorical X, Y, a business problem, which is categorically represented? Let's understand this. You could have a categorical Y. So what can be the types of categorical Y? You could have a binary Y, which could be like yes, no, pass, fail, true, false. So that kind of y could be there. So your y could be binary, or your y could be ordinal, which is like your data could be on like a CSAT rating, like 1, 2, 3, 4, 5, or excellent, good, average, bad kind of thing. Your y could be excellent, good, average, bad. So ordinal y, or you could have a nominal y. Nominal are the rarest out of them. So, but yes, nominal y could be generally used during product launches and stuff like that. So you generally have those brand names listed here. Probably say again, still going with my Reebok, Adidas, Puma, and Nike. So we got like various. We're gonna compare your stuff and see is it influencing the sales of a particular brand and stuff like that. Yeah, we might want to be using such a project. So it depends on you. You don't control the projects. Your management decides the project, what project you will be working on, and so yeah, these could be rare projects that you might come across, but yes, you can get them. So y can be of any type. Uh, if your y is binary, nominal, ordinal, whatever, it is categorical. It is text based. These are categories. Rest, whatever we discussed, this was numerical y. All we were talking about, these were numerical y's. All was y's were numerical y's. These were numerical. Numerical y, which was got converted into normal, non-normal, and within that you had this variance and stuff. So that's what we covered up. Now coming back to our categorical one, if you have a numerical x, then you have three tests and you will use only one. Which test we're going to be using if you have a numerical x will depend. So this is where you have to kind of keep in mind. You can only use one test out of them. Which one? Uh, it will depend on the type of y you have. So if your y is binary, then you will use a binary logistic regression. If your y is ordinal, then you will use an ordinal logistic regression. If your y is nominal, you will use a nominal logic. You because and that's in your y will be same throughout the project. So either y you will be binary, ordinal, or nominal. So either you're going to be using a binary list, BLR, OLR, or NLR. One will be used. Let's take a simple example and we'll be able to get that clear. Categorical y. So this is the data I have, and say, assuming this is my Y, turnaround time target met, yes or no. So my management is probably just tracking a performance like whether did we meet, yes or no. Did you meet a target? Yes. Didn't meet the target? No. If your business problem is categorized as binary Y, like yes, no, pass, fail, true, false, that's a binary Y. So you have your numerical axis, like in this case we have got numerical axis. This one is my numerical x, age, tenure, product per batch. There are three numerical x's I've got. All these three numerical x's will fall into this category. So these are the numerical x's. And what's my y type? My y type is binary. So for this, I will be using a binary logistic regression to test age has an impact on turnaround time, yes or no, whether tenure has an impact on it, whether product per batch has an impact on it. The test will be done, which will be binary logistic regression. Why? Because y is binary. If in case your y would have been, forget about this column now, if your y would have been the NPS score or CSAT score or something like this, excellent, good, average, bad sort of thing, that means it's a ordinal y. Then for these x's, you would have tested ordinal logistic regression, like age versus NPS score, tenure versus NPS score, product per batches versus NPS score. All you would have been doing is ordinal logistic regression. Why? Because your x is a number and your y is ordinal. X is number, yes. And if your y is ordinal, you've got to be doing an ordinal logistic regression. Why? It's dependent on the type of y. Similarly, if your y is in nominal, like product A, B, C, some products, and you want to check whether age wise there is an influence on a particular product sale, or tenure wise there is a sale impact. Product per batch manufactured, does that influence the sale? Well, nominal y, yes. These are the numerical x's. So if your y is nominal and your x's are numerical, that definitely you're going to be using a nominal logistic regression. And the best part about here is for everything else, two groups, more than two groups, all those categorical x's, you have one test only, chi-square cross tabulation. This is also known as test for association. That test will take care of rest of it. So ideally for a categorical y, you'll have only two statistical tests that you'll be doing, because your y will be either binary, ordinal, nominal. So you'll be either using one of them, only one test in a project. So if your y is binary, it will remain binary always. If it's ordinal, it will remain always. So only one test out of this and one test out of this. So in the entire project, you will be only using two tests. And for numerical x, one test; for categorical test, another x. And there's nothing else other than this. So for these, we will be performing the same tests. Now, logically, is that okay with everyone? Are we able to make sense like what test needs to be done before we conduct these tests?
Can you just tell me once again when will we use that chi-square
Yeah.
test?
So it is when your y is categorical. So y is categorical. Either it's a binary y, it's ordinal y, or nominal y. All these are categorical. So they are not numbers. They're not numerical x's. They are categorical. So y can be of any type. Y can be of any type. Any but category. So this is category. This is category. This is category. So it doesn't matter. It's ordinal, nominal, or binary. Y is categorical, and the x is also categorical. So either it's a two groups. This is more than two groups. This is two groups. Doesn't matter. Everything which is text based, everything which is text based, it's all going to be a chi-square. People call it as chi-square,
Okay.
chi-square, every x. So either you only for this numerical x's you'll be doing a depending on the type of x, y, you'll be doing the test. But everything else will be chi-square or chi-square.
All right.
Okay. Are we okay with this, everyone? Just like in case we're okay, we'll perform the test.
All good.
All right,
Thank you.
perfect. All right, then let's move ahead with the testing. I'll just copy paste this data and quickly let's check this out. How does it work out when you kind of do the project, the testing? So we do have some more tests which is lined up before we can sort of say what we are done with the statistical testing. So these are few tests which we'll be covering up next. So first of all, assuming that my y is binary and I have to perform whether uh, age has an impact, tenure has an impact, a product per batch has an impact on this output, which is turnaround time. I am recording my data, my performance as binary Y, like yes or no, true or false, something like that. So that's my binary Y. I will test my, which test I will pick up? Binary logistic regression. Why? Because my Y is binary. Let's go back. Stats, regression, regression, not here, it's here. Binary logistic regression. We click on fit binary logistic model. And here we select the response. Response is turnaround time met. Yes or no, true, false. Well, that's the thing we're looking at. Continuous predictor we are looking at, which is what we need to know. Say the age part. Let's kind of pick up the age. That's what we want. Click OK. It is going to give me the p-value that we are looking for. Yes. For age, what is that we're talking about? Is this a significant factor? Is it null or alternative?
Now,
Null.
Null.
Now, so age doesn't seem to be influencing the output, whether you're going to meet your target or you're not going to meet your target. Age has no role to play. Let's kind of check it out for the other one. Let's say we're talking about tenure. Does that play any role? Let's kind of check this out. It's still null.
Null.
Okay, let's assume the data has changed and like my y is no longer this binary y. My y is this uh, ordinal y, and I'm tracking the data like this is a different data set. Assume this is, we're no longer talking about this binary. Now, if your y is NPS score, which we are recording as average, excellent, and poor, what test would I do for checking whether tenure of the person or experience of the person is that influencing the NPS score that we get? What test would we be doing here?
ordinal. Ordinal
Ordinal,
logistic regression.
perfect, perfect. Thank you. So ordinal logistics regression would be right here, just below that. So see, BLR, OLR, NLR, all of them are right here. So all of them three. So binary logistic regression we have done. Ordinal is right here. Select your response, which is net promoter score. That's what we're talking about. And this could be like a rating also, 1, 2, 3, 4, 5, but it's an order that we know. It's an order. Anything which is in ordinal format. Model will have my x's, which is say which is I have as age or tenure or whatever. Let's look at this one. Whether this has a age. Age, does that have a significant role to play?
No.
No, it doesn't. Let's quickly check this with something else. Let's say tenure, experience of the staff. Does that influence your the result that you see because of the tenure? Is it?
Yep.
It is definitely influencing the impact. If you are experienced or not experienced, that is definitely it has an impact on your output. Whether you're going to be getting an excellent score, you're going to get an average, you're going to get a poor. Is influenced by your basically your tenure. So pretty much we have a root cause at this stage. Similarly, if you assume the data is not like forget about this why. Now, if your data is categorical, if you like you're going for a product launches, market product launches and stuff like that. So I will be also telling you one test which is done before. Like when you can conducting a survey, it's one of the most important widely used tests, which I'll be talking about last technically. Widely used test. Why? Because casinos, like I'm not sure like not how many of us would have visited casino, but yes, casinos have to get a license and to operate and to operate a casino you need to pass this statistical test, and that's this chi-square goodness of it one variable test. This is what they have to prove. Even the match happens when you toss a coin, those coins go through this chi-square goodness of it test. What if this coin is a tricky coin? What if the when you are in casino you're playing those you using those dice, is the dice is a tricky one? Like technically people use that these tests are used for validation globally. The auditors will come and do this test and give you a certificate basis which you would be allowed to run a casino like that. So people globally, the Las Vegas is pretty much they have these tests being conducted time and again, unless and until you have these tests conducted, pretty much you cannot be given the license to operate. It is something which is used for product launches also. When you're doing a survey and you really want to be confident, can I launch this product? Should I launch this product or not? Am I good enough? Like, can I compete with these existing market giants? I have done some bit of survey. So you conducted some survey and you want to check whether you're good to go or not. Uh, that's the test which will give you the confidence whether your product is really that good, and can it really sustain the market pressure when people when you sort of launch the product and you would have existing players in the market. Do you really think your product will sail through? And that's what, so this is like we're going to park it for the end. So this test is used for initial testing, which will give you a clear line of sight, and then you can try out all these product launches kind of categories. Like you can conduct brainstorm, do a brainstorming session, collect some data like this, and then you can do further analysis as to what could be the drivers which could help me do well. So yes, you can do like some companies probably say my product is something, and I would like to compare with my peers, my competitors, and I would like to see what are the things which influences. We could think about some possible x's and we can do some testing. Bottom line, this can only be used, gets generally used when you're doing about generally market product launches and stuff like that. So let's kind of do a nominal logistic regression and stuff like that. We'll get the clarity, but that test definitely will make more sense to everyone. For now, let's do the nominal logistic regression, assuming my y is this a b c. Nominal y doesn't matter, doesn't tell me which one is good or bad. So nominal y, I want to test whether it is influenced by this age or tenure or product per batch. Let's kind of check this out. Stats, we got regression. The last one is nominal logistic regression. So we click on this nominal logistic regression. We want to check whether brand sold, is that getting influenced by like age, the age of the person. Does that influence which kind of brand I would have a preference or not? Well, that's what we're going to be checking this out. When we look at it looks at various categories, it looks into various options. Finally, what we're going to be looking at is the final test slope. See, it tests your various products, like looks at comparison, keeping one product as a constant, another it checks the impact of one product to another. Finally, we're going to be looking at overall slopes. So this is what we'll get 1 year p value because it's testing every product with another. So it get multiple and overall. Finally, looking at everything technically, this is what we're going to be looking at. It doesn't tell me that there is influence. So sorry, the age doesn't seem to be playing a role in deciding like what product I'm going to be picking up here. If it's a numerical X, let's kind of pick up another X. Say we are picking up, say, product per batch. Let's kind of get rid of this X. Product per batch. Well, does that influence? No, doesn't have an influence. So simple stuff. I can see bottom line, we got to keep this basic fundamental in mind. Whenever we're testing this, I got to look at the type of X, what we are dealing with. It's numerical, yes. If your X is numerical, you got to just look for the type of your Y. If your Y is binary, BLR, Y is ordinal, OLR, Y is nominal, NLR. That will help us understand which one is a root cause. That's how we do this testing. Is this okay with everyone so far? I just want to check. Are
Yes,
we
it's
okay with
clear.
OLR, NLR, and
Can you
BLR?
please just repeat the last point about the slope?
Yeah. So basically, let me just quickly show it to you. See, we had how many? Three products, right? So this has what it has done. It has picked one product as constant. Like this is a reference product. It has picked one product as constant and bases this as a constant product. It's testing the impact of age, keeping this constant as impact of B on C. So it says like it uses B versus C, then it uses A versus C. So A, C has been kept constant and basis that keeping the age factor in mind, age is an influencer. It looks at it, does that influence, does that there's is that impact, is that impact, then for overall, then looks at the overall impact. So we look for once the entire regression stuff has happened, technically we look for the overall impact, the test for all the slopes. And it like kind of looks into everything. The overall, do you see age as playing any critical role in having a preference towards a particular batch? It says no. That's what it is all about. So in the end, whatever comes in here is what we got to be looking as a decider.
Okay, so if the p-value is less than 0.05, we will
Yes,
have an impact of one of the products will be impacted by age.
yes,
Okay,
definitely yes.
thank you.
That means age would have a definite impact towards one. Now, but yes, let's do one thing. See, any which ways we're gonna be doing. We'll be working on this categorical one. Like I said, this is one very commonly used. This one chi-square cross tabulation. And when we're doing this, we'll also be doing this chi-square again. Like so, let's kind of get this done right away one time. But chi-square, let's kind of look at the entire spreadsheet. We have got be it your binary y, be it your ordinal y, be it your nominal y. If your x is categorical, like this is x, all these non-numerical x's, all these non-numerical x's, everything is categorical. Be it y is no, binary, ordinal, nominal, doesn't matter. Plain and simple. Is your y categorical? Yes. Is your x categorical? Yes. Simple as that. Two categorical variables, one x categorical, y categorical. Only test is chi-square cross tabulation. So let's kind of have a look at it, how it's done. Stats. This one is in tables. And if you go down, it says chi-square test for association. That's what you got in. The older version like was chi-square cross tabulation. You can do the same test and get same values here also. That's what it says cross tabulation, or you can call it as test for association. Technically, it's the just the updated version in terms of not the testing part, the looks part of it. Like it covers. So we'll go with the chi-square test for association. Same test result, but just a different alignment in this case. Well, row and column put anything, whatever you feel like. Say turnaround time, yes or met, yes or no. Is that being influenced by, say, system operator? Is system operator influencing the person who's handling the ticket? Is that person any which ways impacting the outcome, whether you will meet your target or not? Well, let's check this out. If I click on statistics, it's already tested chi-square test. Well, if I would have gone with the previous version, I have to man the I just want to show it to you the change. what is the difference between association here and the version that I might have was like we could, if we go with this, we'll still get the same value, cross tabulation and chi-square. If I go with this, here I have to kind of give the same stuff. This, say system operator. The only thing I have to kind of do here is I have to specifically enter this and select this test. So in the updated version, this was already selected. So technically I don't have to do this stuff. I can just straight away go to tables. Test for association is already factored in that tick part of it. Just need to put your X and Y. Put anything, doesn't matter. Here, rows and columns, it doesn't matter. Put anything, anything, or like there's nothing called a Y or X. Meaning you put them either which ways, it doesn't matter. Result will still be the same. Statistics, by default, it's selected chi-square test or chi-square test. Different people say differently. It's all fine. Click OK. Now, quickly have a look at this. This is what we're going to be looking at, the likelihood of chi-square ratio. This says there is no impact of the system operator on target met. But I just want to quickly show it to you. What does this mean? What is happening here? And to explain this, well, I rather should explain the, okay, now forget about this test, because to understand this test, I'll rather do the other one first, and just to make sure that we can make some sense here. I mean, this data, we can easily make some sense, and then so we must do the other test first. This one, if we do this, we'll be able to understand the other one. Let me quickly see if I can get some data, discrete data. Okay, all right. All right, so this is some data. Let's kind of, let me copy paste, and then we can try and test that data. Let me just kind of open up and show you. This one is used for the gambling part I was talking about, the coins and everything. This one, this test, chi-square, one variable. There's no X and Y, one variable. This is also called one variable test, goodness of fit test. Now, this is, say, some survey was done, and people before going for election, or probably before casting their vote, or people before, like after casting their vote, were asked this question. I'm sorry, you had a question, Kanika? Okay, okay, I guess then. Okay, so people were asked this question, like, is there a specific preference do you have? Which party do you like? So some people said like, so randomly we had some surveys which could be collected. So Democrats, we keep asking people and random selections been done. So somebody said Republicans, then others, then somebody said Democrats, and Republicans. We keep collecting data, keep collecting data. So now what we have got here is some survey details. Now we would like to understand, is there a specific preference? Like when we selected the candidate, had the audit done, the survey done, every party, so we technically can see there is Democrat, Republicans, and some other category. Everyone had an equal probability of being picked up or chosen by the candidates, by the people. Everyone had equal probability. So what this one, it tells you that everything has an equal chances of being picked up here. So let's go to tables. Here it's chi-square goodness of fit test, one variable. And let's click on this. Do you have categorical data? Yes, this is the categorical data. You pick up the preferences here. Equal probability, everything had equal probability of being picked up. So people, when we interviewed somebody, like there was a free level playing ground for everyone. Everyone could have been picked up. And I want to check whether, is there a preference for a particular party in the audience? Like, am I understanding that everyone has a fair chance? Do we really have a biasness of a particular part, like of the people towards a particular party or not? Let's click OK and see. This is what we found. Like we got like 36 odd people. No, let's just kind of get rid of this and have a look at this one. This is what we are going to be looking at. So the orange one, or whatever this color is, it says expected. So every party had an equal probability of being picked up. Every party had an equal probability of being selected or chosen by the people. So equal probability, equal. So whatever number of people we interviewed divided by 3, that's the probability of every person. So every party had equal chances of being picked up. Against that, what did you see? against equal probability of 133 people would have should have chosen Democrats. We found 203 people preferring Democrats. Against expected number of 133, we had only 83 people who preferred the others. Against the expected of 133 people choosing Republicans, only 114 supported Republicans. Do you see a difference in observed versus expected frequencies? Yes. Is that a large enough difference? And can you confidently say that people are preferring more of Democrats and this time Democrats will win this election if it's a large difference? And this difference can be concluded for the entire population. We've done this survey from different areas, and we collected this survey, and you see this data. I do see a difference, but is that a large enough difference? Can you confidently say that Democrats are going to win this election this time if this is a large enough difference? And can you confidently say this about the entire population? That's what we're going to be seeing here. Let's have a look at this. There were 203 people who observed, that is voted, like what said, they like Democrats, 83 others, and 114 for Republicans out of a survey. Everything had an equal probability of being picked up, which means that everyone should have got 133 counts, 133 counts. So this was expected. This is what we saw. Do you see a difference? Yes. Is that difference large enough difference? Yes, absolutely. So you can confidently say that Democrats are definitely going to win this election this time and by a big margin. The difference you see is not a small difference. It's not by chance. It's a major difference, and you will definitely see them winning this time. And that's what, let me kind of relate this with some other example so that we all can relate with this. Say, okay, let me create like a small test here. Now, say I am gonna like, so I'm not sure how many of us would relate with this cold drink brand. So cold drink blacks, we all, I'm sure, relate with Coke. We all understand Coke. I guess we all know Pepsi also. So I'm not sure, like, because different countries have different specific brands. We have one in India, which is Thumbs Up. I'm not sure how many like other countries have it or not. And say I want to launch my brand now. That's where my brand comes in the picture. This is my brand. And see, these all brands are of like similar flavor, more like similar flavor. They're not like mint based. No, they're not mint based. I want to check whether they are really good. Like, so I'm going to launch my brand. These are existing brands and pretty popular. They have got their own market share. I want to check. Well, I definitely want to get into this market. I want to check, is my product really worth launching, and can it really compete when I launch it? So we did a survey, and we did a survey. We had a strategic, we had few strategic locations. We had some supermarkets, some colleges, universities, wherever there's like a lot of people who gather at different locations, and we got survey collected. Now this is how the survey looks like. Let me just kind of randomly put some values. So people keep coming, and they kept on saying different stuff, and we'd like to kind of thumbs up. Okay, well, that's, I kind of messed up with the spelling in images. Images, that's fine. Let me just, so some survey happened, and this is how it worked out. Pepsi. This is Coke. Oops, this is my brand. Maybe different people, and how this testing was done. Let's understand how this testing was done. So people would not know what they're tasting. So if I love Coke, I would, if I know the sticker of Coke, I would have a biasness. So then I would not look at any other thing. So what we do is we'll be pouring this in glass, and that's how it's done. I know what's the glass number one, what's glass number two, what's glass number three and four. Everything looks same, but so when the people would be supposed to kind of sip it and finally tell us that did they like glass number one, two, three, or four. So even the beauty products, they actually do this testing and survey when they launch their product and stuff like that. So say survey completed, we got some survey done, and would like to say whether this is my, say, mint cold drink, whether this is No, because there was a fair chance everything could have been picked up because we ensured that there's no label. Everything was like everyone, every mint, every drink had an equal probability of being picked up. Let's see whether whatever we got as a result. So let's kind of get rid of this. Okay, because we did whatever number of surveys, the total number of surveys, every drink should have been picked up like 27.5 times. 27.5 should have been the average count of every drink, every kind of expected. What you observed was this was just notch up 28. My brand actually got 43, which is great. Uh, Pepsi did little low, and same goes for thumbs up. Do I see my brand winning this race? Definitely yes. But this is just a sample, a small sample from a small population. Can I take this as a evidence and can I go for a launch? Can I be confident if this is a big difference or not? Let's kind of check this out. Looking at it, like we had like 20, every, this got selected 28 times, 43, 20, 19 against an expected frequency of 27, 27.5. Is that difference a large difference? Absolutely yes. Please go ahead and launch your product. It is definitely a significant difference. Your product be liked by the people. I obviously, when it comes to the market, people will say no. People would have their preferences, but your product was preferred over others when people had no labels. So technically, they liked the flavor or whatever, and definitely you would. It might take some time, but you definitely will be there. You will get there. So it definitely has an edge over others. Please go and launch your product. That's how it works. The goodness of it one variable test. Now, based on the same logic, the goodness of tests that we talk about. So even the chi-square, because it's again a chi-square thing, the category versus category, when we do this chi-square test for association, so that's what it looks into. So if I do turnaround time versus system operator or in turnaround time versus process complexity, what again here it looks like, it looks at it is observed versus expected frequency. Again here also, this was expected. So Binny was expected to deliver, like based on Binny's performance, we expected that Binny uh, would have like failures of like say 59.14. Against that, we had a failure of 64. We were expecting failures, which is no, 58 for Jay. Against that, 58, like so somewhat. There is some difference expect observed, and so this was expected, and this is what we got in terms of no. In terms of yes, this is what we expected, this is what we got. Do we see a difference? Yes. But the question is there a large, is this difference a large difference? The answer is no. Unfortunately, whatever your difference, this is not a large enough difference for you to conclude and say that yes, it is a root cause. Sorry, we cannot prove that yet. Let's kind of take up a different X here. Say, forget about system operator. Let's pick up say process complexity, whether process complexity impacts the outcome of yes or no. Doesn't. You had 129 failure expectation of 129, you got 133 failures in level 1. We expected 163 failures in level 2, against which you got 160. There is small difference here. Again, similar stuff. We expected 111 to pass and we got 108 pass. We expected 140 to pass, we got 144 pass. Is there a difference? Yes. Is that a large enough difference? Sorry, it isn't. So bottom line, if it can be any Y, so forget about this turnaround time. Let it be NPS score. Is NPS score impacted by the process complexity? This is also categorical. That is also categorical. Let's test this. No, the NPS score, whether excellent, good, average, bad. You might see a difference, but yes, the question is that a significant difference or not? That's how we figure it out by doing a chi-square testing. Is this sort of okay with everyone?
Please, what's the other p-value above this, the
Above
Pearson chi-square?
Pearson chi-square. So they are like, see, there are a lot of people who have actually tried and tested. When you do test, you get like a lot of them. In the end, see, basically what it does, we have like this would you would never get this as a this turning as or null or this turning as an alternate. No, anything which is valid and different people have different perspective, like how people completed the thesis of giving the result. So different, there could be different tests which can be done. Like we remember, we did a normality test. We had an option of doing it through Anderson Darling. We had an option of doing it through Kolmogorov-Smirnov, and the other versions were there. So similarly, these tests are also valid. So you can refer to these values also. This is nothing. It will be slight difference. It will not change the
Yeah,
verdict
it's
of the
only
test.
very the
Yeah.
difference is very
Absolutely. So this is like,
negligible.
so absolutely. So you can even refer to that. So there's nothing wrong in it because it will never be a drastic difference. It will never change the outcome, and that's why they're acceptable ones, and there are the slight differences which we will still be fine with it. So there's no difference there.
Thank you.
Okay. Coming back to the tests that we have here, so this is like, that's the test we do in terms of finding the, so if we know these tests, we have covered this test. So technically you can get any data in your analyze phase, you would know what test needs to be performed to find your root causes. So if your data is normal, non-normal, or categorical, you would always have your answers. Root cause identification will be done. This is what we need by the analyze phase. Getting into the improve phase, it's just about improving your process. So you have to get your strategies in place, and for that, again, technically there will be like a lot of help taken from the subject matter expert. Because remember, the reason why I did the Six Sigma project is because we had no idea where to start from. We had no idea what's my real root cause. The reason why I did a Six Sigma project is because we had to find out what's your real root cause. Because now you got your real root cause, you can just hand over the process to your process experts, as subject matter experts who understand the process better than anyone else. Let them handle the process and solve it for you. So that's what happens in the improve phase. The role of Six Sigma professionals goes down significantly low, um, and the process experts will draft the solutions, will create the solutions, and sort of implement them, the solutions for you. That's what we do in case of improve phase. Now, few things we do from the perspective of improve phase is what we're going to be discussing. It's what's our role in improve phase, again from statistical background. So process experts, when you give them the reasons, they know the process challenges, they will be implementing solutions, they will be trying and testing solutions. uh, they would know it because they are functional experts. But where do we help them? What's our role in the entire journey in the improve phase? Because till now, we had a role to play, which wherein they were sort of not actively involved. This phase is their phase because it's their process, their business. They understand it better than us, so they would take up the lead here. They would take the front seat, but we do have a role to play here also, which is more about regression. So in the improve phase, the moment you know your root causes here, you can try out with regression. Wherever you got a numerical access, you can try out regression. Now regression is something which is going to help you understand what can we do with that x, how much changes do we need to make in an x to get a desired output. So let's have a quick look at regression stuff, and we should be okay with that. Let's kind of have a look at this. So regression we will be doing this. Give me one quick second. We have, okay. So in regression, we'll be talking about a simple regression and a multiple regression. Now, in simple regression, what we do is we test one x with y at a time. We get a p-value, we get r square, and we get a linear equation. Here, we test multiple x with y. We get p values because we get multiple x's. We look at r square adjusted, and we get linear equation. So same similar stuff we do in the before. See, technically this the process experts, when they start working on it, it's important to tell them like what's the importance of an x. They would definitely know it, but whatever we can add to the knowledge base, it will help them. So let's kind of look into this a small example, and we'll be able to make some sense here. Let's kind of get rid of this sheet here. So I have some data around this. Let me just get rid of the gender here and the numerical x's I've got. Okay, here we got. Go. Let's try and understand what like this the entire purpose of this data. So the business problem here we talk about is my salary. The business problem is my salary. We would like to predict the salary. We want to make sure that we can make some logical reasoning about the salary we have got. So our process experts have believed that salary is really like impacted or related with, say, interview score. This is my interview score. When somebody gets hired, that's a root cause. How well do you do in your interview? That will significantly impact the salary that you make. This was one perspective of the people that were doing this assessment. Second perspective was how much of experience do you carry? That will influence the salary decision. So just an argument sake, here we got two x's and this is my y. I would like to understand. So we filtered those x's, we figured out which one are real root causes, we got our root causes. Now we further want to understand what to do with these x's. So technically, which one is bigger x? If it's a bigger root cause, we would like to work more on it. If it's a smaller root cause, we would like to sort of work lesser on it. So we can emphasize more on the x's which have a significant impact. So when we do a simple regression, we test one x at a time. So stats, basic statistics, sorry, regression and fit regression model. So in the response, we put in the salary. In the continuous predictive, we put in the interview score. So one x with y at a time. That's what we do. Click OK, and we get few information that we'll be looking for in regression. Number one, we get this p-value for interview score. It tells me that this is impacting the y, which is definitely, I look at the p-value, it bases this. It helps me understand there is a relation, definitely. I look at R square. R squared says 52.98%. So I go back here. Let's say we talk about interview score. It R squared is 52.98%. This is what it says. And then it gives me a linear equation at the bottom. So we'll park this equation because it doesn't make sense when you do it with a single x. When you merge multiple x's, that's when it makes sense for you to can read the equation. So we will skip this now because it will get repeated here in which ways. Let's try and do it with other x. So remember, we have the other x, which is experience, and we test this. We get the three values back here. We get a p-value for experience, which is says less than 0.05. There is a root. It's a root cause. It's impacting the salary. Yes. R squared says 83.26. So experience says 83.26. That's the impact of this is what R squared tells me. And then there is an equation. So we'll skip the equation for single ones. We club them together when it makes sense to look at the equation. What is this R square? What does this R square tells me? Now, when we talk about R square, it explains the degree of variability x explains in y. In a layman language, how much of impact x makes on y. So it tells you how big is the root cause. In this case, if I look at this, that means experience has a very much like it has a high influence in deciding salary as compared to interview score. It has an impact, but not that bigger as interview experience. Experience has a bigger role to play uh, than the interview score. And if we want to further take it away, like to the next thing, we can go for multiple regression when we can do the testing, both of them together. So putting interview score and this together, I click OK. Now, here I will be looking for all of them together. So experience and interview score p-values, both are significant. We already know that. Now we know the individual impact. We already know the individual impact, how much each X is impacting the Y. But during the interview process, you're offering the salary, and these factors are putting their efforts, like their impact at the same time. So experience is influencing the salary decision at the same time. So would interview score would influence the salary decision at the same time. What is the overall impact? Because the individual impact we know, but that's not happening in silo. Interview process is going on. The candidate is sitting, you're talking to the candidate. The guy has some experience and got like has some bit of interview experience you have collected. Everything is playing a role in deciding salary. What is the overall impact? That's what when we do a multiple regression, we look for overall impact, which is 88.78% in this case. So 88.78% is the overall impact, r square adjusted, which is the collective impact of the excess put together. That's what you know by this one. Now moving on to linear equation. That's what we were working for. Linear equation. Linear equation basic fundamental. Here we talk about it is referred as y is equal to c plus mx. That's what we know. Y is your y, which is the business problem. C, if I go by the like a layman language, C would be a constant value of y in absence of x. So what is the minimum value of y? Now, in a like if you want to be technically correct about this is called as intercept, and we'll look at that. M is basically the multiplier of x in layman language. Multiplier of x. This is what we have as multiplier of x, and again technically correct, we call it a slope. X is x. So if I were to kind of get this equation here and try to solve this, let's kind of have a look at the equation. What equation do we get here? This is what it gives me as an equation that you can predict your salary basis this equation. If you work on this, you can get your salaries identified. You can know that how much salary to be offered if you have candidates coming in. So you can use this equation for predicting the salary. What it says, 53.22, that's your constant value. So 53.22 is your constant value plus 1.754 times years of experience. This is getting multiplied by the number of experience, years of experience. So I'm going to keep this here blank because I don't have the experience here. So that whatever value we have, we put in for experience, that will be multiplied by 1.754. 1.754 experience means 1.754 multiplied by experience. So whatever value will be there, it will get multiplied by this plus 2.105. That's what it says is the multiplier of interview score. That's what we have, interview score here. Interview score. So whatever we have as interview score, that score will be multiplied by this value, which is 2.105. And in the end, you have the final salary that you need to offer to the candidate. So it's a mathematical modeling which we're using to predict the y. When you change the value of x's, your y will be decided. Like say, if a new fresher comes in just out of college, no experience, experience 0, scores 0 out of 10, index in the interview scores 0. So nothing changed. This multiplied by the 0 remains 0, this remains 0, 53.22. That is what we talked about. Constant value of y in absence of x. When x is absent, minimum value of y will be constant. So constant will be your minimum value of y. Let's assume that this guy comes in, has some bit of experience, like 5.5 years of experience, and scores say 7 out of 10 in the interview. You have your salary predicted. You should offer this salary. This is the multiplier of this x. This is the multiplier of this x. Somebody comes in with a 9 years of experience and scores say 4.5 out of 10. Your calculator is ready. Now, keep in mind, the only thing you have to keep in mind while you're looking at and creating such a calculator to predict your y, that it is always going to give you the meaning which is correct, and it will be relevant till the time you're working within these limits. The limits would be the maximum and the minimum that you have used here. So I guess you can't, it's a number of years, say number of years of experience. We've got like 20 years or 21 years, I guess, in this maximum. Yeah, 21 years is the maximum. So yeah, till 21 years, you can play around with this experience. I can have it for 15 years and stuff. Well, I cannot use this calculator for 23 years because 21, or no, I can't use it for 22 years because this was never planned when you created this calculator. So till 21 years, it is good to go and offer you the salary. You can use and trust this equation coming from the data. Are we okay and sort of clear with this regression so far?
I'm just curious. What if we don't have Minitab? How can we get the constant?
You can easily get that. Let me just go back to Excel. Mm-mm-mm. Where did we have this file? Yeah. Okay. You got to do one thing, couple of things. Just have a quick look at this. Let me just get rid of this file, like this one here. So first of all, you have to go to your file. Go to, I guess, options. In the options, you have to go to add-ins. And in add-ins, I like my analysis toolpack is active. So if your analysis toolpack you have not activated, it will be showing up in inactive applications. You click on anything here, like in anything, bottom line, and here just click on go. Excel add-ins go. It'll open up this box for you. Select this analysis toolpack and click OK. Now what will happen in the data tab? This data analysis toolpack will come up. And I click on this data analysis, and what we're doing a regression here. Go to regression, click OK. Y range, what is your Y? This is your Y. Okay. What is your X? Your X is here. Do we have headers? Yes, we have taken the headers. That's it, I guess we should be fine. This is what we had. R squared adjusted. This is the one value we got. R squared adjusted. 88 points. That's what we got there. Uh, this is the p-value for overall the regression part. Let's look at this one. Intercept. This is 53. That's the value we are talking about. Intercept. This is 2.104. This is 1.754. This is exactly what we got there. We look at this equation.
Okay.
This is what we got there. So, but yes, Excel has a lot of limitations. You can't do everything here. So yes, there will be limitations that we will be working on. Excel doesn't give you everything what we need, but yeah, whatever we can definitely try out on Excel, but not everything will be possible because technically it is getting better, but definitely, yeah. So you have 53.22, so you gotta like look into it again. That's what we can do. This is, I guess, that's what it is, and this is 2.104. Cut it down. This is what we have, 2.104. This is what we have here. That's the experience, and you can create this equation from here because it's for same values.
Okay. Thank you.
Okay, my pleasure. All right, so moving back to the data. Now, uh, when we got into the stage of improved phase and we're trying to improve the process. Now, technically, it's the role of the management to kind of get into it and get this process, try and test certain strategies, action plans. So it's more the subject matter expert's role. But when they are doing these experiments, now we do have the responsibility there to statistically check and validate whether the improvement that you're seeing are relevant, they are statistically significant or not. Did you really see the improvement or not? How do you check that? There are certain statistical validation tests that you have to do, which is target validation test, or a series of some target validation tests, which we will be doing depending on the kind of data we are going to be dealing with. If you're trying to, if your target has been given to you by your management to increase the average of your process, to improve the average productivity, average of something, then you got to be doing a one sample t-test for checking that did you meet your target, average target or not. If you were given a target to achieve some median goal, not the average. If your management is clear about mean, median, stuff like that, well, then it might have given you a target on a median basis, that this is the median that we have to achieve. Okay, that's when I will be using a one sample sign test. If the target, if you know, like they was talking, like if your boss is finicky and clear about stats, then could be the person could give you a target based on standard deviation. This is your standard deviation target. How do we check did we achieve the target? One variance test. If your process, if a target has been given to you on the basis of count of something, like number of errors, number of parts manufactured, count of something, then you will be using one Poisson rate test. If your target would have been based on percentages, like last year, this percentage, our target is to increase a percentage from say 90% to 95%. If it's percentage based, then you will be using a one sample proportion test. So depending on the kind of target it is assigned to you, and you can't get anything out of this. So pretty much all types of data types are covered here. So if depend like whatever data type you have, accordingly you have a test that you have to do. This is for checking that you did your process actually meet your target or not. We'll do this test right away. We'll understand that. But remember this thing, mean based target, median. So we just got to keep basic fundamental in mind. Once you are able to validate that the target like has been achieved by the courtesy of these tests, when you perform the test, you're able to find out that the test target has been achieved. Great. My project is successful. The pilot process, the pilot run. You've never done a full throttle implementation. You will always go with a pilot scale implementation. When the pilot scale implementation is done and we know for sure the target has been achieved, we have a statistical proof for that. Now, we will be showing a before and after analysis to the management to showcase that, yes, this is where we were and this is where we have reached because of the test. So we will be showing a before and after of the so old y versus new y comparison. If you it's average based, so wherever the data is based on target is based on average, an old and now new y comparison will be done on paired t-test. If it's an old and new y based on median, then you lose a Man-Whitney. If an old and new variance, it will be two variance. Old and new count will be two Poisson rate and two proportion for two percentages, comparing old percentage versus new percentage. Just to showcase, yes, the difference you see between old and new is a statistically significant difference. That's what we do in case of your old and new testing. And once we do this test, again, practically this, along with this test, you will be submitting something else as well. So before and after test you have looked at, so you know when you're going to be submitting at this stage, when you know your process has achieved the target, you will be definitely putting this on a PowerPoint slide to showcase to the management to seek an approval for full scale implementation. Okay, so one slide probably can have the these results that you have achieved the target. One slide could have your before and after test results. Other than this, what you would be adding in before and after box plot of your process, Y metric, before and after control chart. We haven't studied control charts though, but right now we're kind of discuss before and after sigma levels. And then you would have cost benefit analysis. So now, honestly, that's not something what we work on, but because the finance guy from your team will be working on this, it's not what Six Sigma professionals would be required to work on, but we should know it doesn't shouldn't sound like an alien thing to us. So yes, basically NPV, which is real net present value, then we have IRR, then payback period. So generally the cost benefit analysis done on these parameters. So we'll talk about them. That's when you kind of sign off and say, well, the management gets the report that yes, you have improved the process on a small scale, pilot scale. You have proof and validation for that, before and after case study for that. Well, it makes financial sense to go ahead and implement the entire solution on a full scale. Go ahead. That's when you get full scale implementation approval and you go full throttle from here on. So once you get an approval, full scale implementation is done and all steps are repeated. So bottom line, you probably just improved a small portion. Now you just replicate this. So this will not take time, because more like you have improved a small segment of the process. You already know the recipe. It's just about now going full throttle for end time
rolling out the change for entire process. You have done it on a small scale. We have created a prototype solution which works, and you have proof, a validation for that. And you, this doesn't take long for going a full throttle and then ensuring that is done. And then you have a proof and validation that the entire process has improved. Again, you got to be doing this same steps. So all same steps will be repeated. When your overall process has improved the process target, well, good job. The it will be marked as the improve phase is over. So pretty much we need to yet work on these steps. But is the flow okay with everyone? Are we all able to make sense with this structure, like what we discussed so far?
Yes,
Yes.
it's
Oh,
clear.
okay. So okay, would you guys be okay with it? Like, shall we take a 15 minutes break now because we want to be starting something new and just want to be sure that everyone is clear about it because this is last series of tests. Is it okay? Everyone is okay with 15 minutes break now, and we come back and resume from there.
Yes.
Yes.
All right, then
Yes.
let's connect in next 15 minutes from now.
Yes.
Right. Thank you.
Okay, thank you.
Uh, yes, are we back from the break? Would request you to please confirm in case
I'm there.
we're back. All right.
Yes.
Perfect. All right. So let's get started then. Okay. Now, while we like before going on the break, we were just briefly discussed about uh, the regression part of it. Now, with reference to the when say when the process is uh, like we already know the root causes, the process experts would sort of frame some bit of action plans to understand like what can be done when they're working on those action plans and they're implementing those action plans and strategies. What we're going to be doing is collecting data to understand if the improvements are actually happening. If the improvements are happening, you will be able to understand by these target validation tests. So I'll just open this up and let me quickly. So I'll place these files in the Google Drive for you to kind of have access to. So how do you do your this one sample t-test? So like this is what we have. So if we technically you need to understand only one test and the logic will remain same for all of them. So if you understand one, we all just need to know what is the name of the test and the language will change. Here we'll be comparing the mean, here we'll be comparing the median, standard deviation, and so on and so forth. Logic will all remain same. So just need to understand how target validation test works. That's what we need to understand here. Just quickly have a look at this. Forget about this. Let's like look at the progressive validation here, and that should kind of give a perfect understanding here. Let's have a look at this one. Okay. See, my management wanted me to start a project and increase the daily productivity, average production. That was supposed to be increased because of the various strategies. We figured out certain root causes. We make our action plans. We're implementing those strategies. But we're checking that we want to check whether is it did we achieve the target or not by virtue of the strategies. So say in this case the management had given us a target that you need to increase the average daily production beyond more than 425 kilograms per day. So some sort of manufacturing unit. So whatever may be the target, here it's like 425. So at the end of week one, so you just have this week one data. And after you have implemented the strategies, 1 week have gone by, you want to check whether did we achieve the target or not. So I go back here and I collect the data at the end of week one, and I want to check whether did I meet the 425 target or not. So how do I do it? Stats, basic statistics, and one sample T. Click on this one sample T. I select this week one data. That's what I have. Perform hypothesis test. What is the target? 425 kilograms. That was given by the management, and we want to achieve this. I click on options. Now, it's asking me, what do you want to prove? In this case, so please let me know what is that you would like to prove here. First one, second one, or the third one? What is that we're trying to prove here? Is it, are we going to prove the first one, second one, third one?
Third one.
The hypothesized mean is 425. So first, second, or third? Sorry, I didn't get your voice clearly.
The first one.
Uh, are we trying to prove that the average of the process is less than 425?
Oh,
Third,
third
sorry.
one.
More than
Third one.
Third one.
425.
Yes, yes,
Third one.
absolutely. So my intent in this project is to increase the production. So yes, you rightly said, I would be proving a point that yes, because my strategies are so good, my action plans are so good, and we have followed up and stuff done stuff, we have improved and we have overachieved our target. That's what we would like to prove. So yes, the third one is mean of the process by courtesy my initiatives and strategies. We've increased the daily productivity more than 425. Hypothesized mean is 425. That's what we're talking about, hypothesized mean. Let's check this out. What does it tell you? Null or alternate?
Null.
No.
Null, absolutely. Sorry, not yet. So we haven't been able to achieve the target. Null is 425 versus alternate, which is greater than 425. We want to prove that's greater than 425. That's my alternative hypothesis. Null says equal to 425. Sorry, this is not, like, we have not been able to prove, we have not been able to achieve this 425. Okay, perfect. Let's learn. So we learn from the mistakes. Nothing happens overnight. So every good thing takes time. So similarly, this, we would have learned from the mistakes from week one. We would have seen what needs to be improvised, would have made some changes in our strategies, and we would sort of have gone ahead and collected data at the end of week two with the improved strategies. So we perform the same steps at the end of week two. We again collect some data and to track the performance, the progress. Is it getting better? Same 425. You still want to prove it's greater than 425. The end of week two, we again get a null. Okay, that's fine. Let's go ahead and check. Week three. At the end of week three, we are able to prove it is null or alternate.
Alternative.
Alternate.
Yeah. So we have a statistical evidence that the process average has significantly statistically changed, and it's not a matter of chance. It is going. It has the DNA of the process has changed significantly. We just talking about few data points, few samples, but based on this, we're able to predict that the process has significantly and statistically changed. Once we've done this, pretty much what we can do is we can collaborate everything together to make some sense here. So we can put together week one, week two, week three all together. And that can, so it may be more like week three, week four, week five, depending on what project, but you have all the journey. You can showcase at one go. And if now let's see, this is the entire study. Let's see what it has to say. First week, we know that the average we didn't get, like we didn't meet the target, it was null. It says for this 19 samples that you're auditing, the average is 237. And there's a likelihood that your average, obviously, when you pick more samples, less samples, you pick up a different sample, these averages will change. And there's a chance that your average can go down up to 224. How confident we are? 95% confident that your averages can go down up to 224. Well, that's what we got. It's way off from 425. So, sorry, null. In the second week, uh, our average was 354. We're 95% confident that the averages will go down, can go down even up to 330. So, which is way off from 425. Still null. Third week, our sample average was 463. But we're 95% confident that this average, obviously, if it will fluctuate, can get more or less. My concern is, well, the lesser side. The lowest it could go up to is 442. Well, that's great, because the lowest it could go is 442, which is much higher than 425. So the DNA of the process has significantly statistically changed. That's the evidence. We know now. Know 463 is what is my current sample average. These averages will fluctuate. If you pick more samples, new samples, it will fluctuate. The lowest you could get is 442. Great. You have definitely increased and you have statistically significantly improved in your process. Let's look at another example. This will get even clear. Let's have a look at the other one. Another example, which is about reduction of ticket closure time. Reduction of ticket closure time, which is like we got 3 weeks data. The management wants you to reduce the ticket closure time, and the target is 13 minutes. We have to reduce this ticket closure time and bring it down to less than 13 minutes. So we follow the same process: stats, basic stats, one sample t. Let's do all of them at one go. Week one, week two, week three. The target is 13 minutes. And now help me understand what is that you will be choosing it as alternative: first, second, or third.
First one.
The
First.
first.
Thank you. Thank you. You're absolutely correct. First one. We want to prove that it's less than 13 minutes. And let's look at them all together. Have a look at this. This first week, we picked up 36 samples. We got an average of 16.528. Our concern is that we want to bring it down less than 13 minutes. What it says, there is a likelihood that upper limit, this average can even go higher up to 18 minutes. So null. Sorry, you have not achieved the less than 13 criteria. In the second week,
we got an average of 12.111. Great. Your average has gone down below 13, but this is just a sample average. Will it change? Yes. It tells me that there is a probability that it can even go higher up to 13.4. Well, there is a probability that it can cross 13. Although the sample average has gone down significantly, yes, but that is just a sample. It will keep changing. And there is a probability that it can even touch 13.4, so that you cannot say that it has definitely going to go below 13. No, there will be some instances when it will cross 13 also. So you cannot say that your process has definitely changed. No, there is a probability that it can go higher up. That's why you're still null. In the next case, yes, it has gone down, and the maximum, the 95% probability is saying like maximum this could go up to is 11.9. Well, there is any given day you'll be less than 13. Perfect. You are safe. At this stage, you can definitely declare we've gone through this transition. The process has gone through week-wise transition, and your process has significantly statistically changed. Are we okay with this, everyone?
Sir, just a question. In case on week one we see the improvement, do we need to continue and monitor for two another weeks to make sure it's standardized?
No, the target once achieved is achieved, and that's the standard
Okay.
will happen in the control part. The moment the target has been achieved, we have an
Okay.
evidence, then we can stabilize this using the
Mhm.
control charts, because these would not be like a fluke, because based on the sample, it is looking at all those probabilities also. It's not about sample. It's looking at the entire probability. If you have been able to improve in the first week, great job. And technically just stabilize it. You've got to make sure that if it's improved, let's ensure it stays as it is.
And here the sample size is the same as at the initial sample size
No,
for
this could be small. This
validation.
could be small. No, this could be small. You could take it like at least you see these t tests. And there was a question yesterday. It was asked like, what are? Let me quickly go back to this so I can mention this somewhere. So when we talk about, there was something called a z value you were looking at. There was a t value, or there was a f value and stuff like that. So when we talk about z, when the sample distribution is like more than 30 samples, then you talk about z. The distribution is called a z distribution. T is less than 30 samples. So all this while when you talk about, this is T table. So this is where you're talking about less than 30 samples. This is why because when you're doing an improvement, you cannot that like you need to do a frequent testing. So yes, frequent testing, you need less than 30 samples. So all this one sample T, two sample T, we did all those TT part of it, even Anova, we can work with very, very limited samples. So, and then we can get our results. So for validation proof, yes, you're good with it. So less than 30 samples will work absolutely fine. So in our case, if you have more than that, then it's absolutely good. Less than 30 samples, you can still work with it. So you could have 10, 15, 20, 30 samples, whatever works best for you. 30 or more will any given day be better, because the data gets more clear and better when it's consumed. Like when 30 is the benchmark, when technically we look for at least 30 samples. If it's less than, like, so we even work with 5, 7 samples also. That's also there. So T distribution comes into place for smaller samples. Z is when we're talking about bigger samples comes into picture.
Thank you.
Okay. Moving on to your the next series. So we talk about one sample T. Similarly, exactly on the same logic. Nothing, no logic will change. Just the name of the test will change, which is one sample sign. So assume this is one sample sign based state testing, and we want to test on a basis of median. On the basis of median, the name of the test is one sample sign. If your management has given you a target of median, non-parametric, one sample size. That's what it is. That was mean based. Here you will be comparing with median. So say week 1, week 2, week 3, whatever target has been given to you. What is the test median? That was a target mean. This is the target median. So whatever is the target median, you will just put it there. Say target median is 13. I don't know, like I'm just randomly putting. What is it you want to prove? Is the target median has gone less than something or more than something? That's what. Same logic. Nothing is changing, just the name of the test is changing. If you know the test, you're done. Bottom line, it helps you to understand Is it or not? So p-value same logic will come in here also. I hope that makes sense.
Yes.
Yes.
Logic is will always remain the same. Like it's just about the testing part, which we should know the process about it, of dealing with it. Similarly, if you have variance based testing, then it's a one variance test. So one variance test will be given a target in the language of standard deviation or variance, which is very very rare. But yeah, still, if you want to find it out by one variance test, this is all in here. So stats, basic statistics, you got one variance test. It's based on a target. When you've been given a target, select the data. So say, for example, this is the data. I don't have the value of standard deviation. So if you have value of standard deviation as target, whatever it is, so either I calculate this. Let me see. So what is the standard deviation here? Say week one data. Some let's find out the standard deviation. It's 5.417. So let's see. The management wanted to reduce the standard deviation to 2.5. That was the target. Did we achieve the target or not? Let's kind of check this out. One variance test. Select the weeks, all the weeks, and see did we achieve the target. So perform hypothesis test. Standard deviation of 2.5. We wanted to reduce it from say current like say 5 or 6 standard deviation to less. So variation has to be reduced. What is that we want to prove? Standard deviation is less than hypothesized mean. We want to reduce the standard deviation. Let's see, were we successful or not? Well, it tells me whether we were successful or not. Looking at this, they are looking at various values. Like, and let's have a quick look at this. If it takes like there's a chi-square method which is used only for normal distribution, and bonnet is used only when we talk about continuous data. So we need to know what kind of data we're testing, because continuous data is only for measurement data. Normal distribution can be for anything. It like so any number numerical data can form a normal distribution there. So we can use if it's a measurement data, we'll look at the p values for bonnet. And if the data that we are working on, it says some count based data, something which can be any number, then we will be using a chi-square method. So but in general, a chi-square method will be more robust than the bonnet one. More robust. Chi-square method like is more applicable every time. But still, if you want to be very very particular, very precise, you can go with this bifurcation. Let's look at this. So week wise, it has looked at standard deviation week wise, and then finally, and pretty much you would not be getting any result here because I don't think it's gone below that test results. So the chi-square method, like so overall, it is testing every week by week. Uh, chi-square it says null, 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 null. So every week the chi-square or bonnet method here has always given you every week you've been null. So if I want to probably it has it gone below? No. So let me put down a target of say 3. Let's see what does it tell you now. Still it's not a significant one. If the drop in the uh, standard deviation is not a significant one. So if you hear, even in this case, you're getting a p-value which is null, null, all null. So bottom line, if you are given a target in the language of standard deviation, that's the test. So one variance test will be used when you're dealing with a target like this, variance based testing. Are we okay with this?
Yes.
Okay. Let's have a look at this poison target evaluation test. I guess we have this file. Okay. Uh, they say there's a department which is concerned about number of complaints are coming every day. They want to plan their staffing, and they, as per their understanding, till the time the complaints are, the rate of complaint is up to 20, they can work with existing staff. But if it's more than 20 complaints, then pretty much you uh, probably need to hire more staff. So the current staff, they're understanding like we can handle up to 20 complaints. Somebody has been asking within the department that need more people. There have been more complaints of lately, and they need more people to handle those complaints. So null statement says the complaints is equal to 20. The count based is one Poisson rate. The alternate statement, probably we want to prove a point that no, the complaints are more than 20 on a given. Let's kind of have a look. Let me quickly check this chat. Continuous distribution is basically anything which is based on measurement data, like height, weight, time. That's kind of distribution. Anything which is continuous data. Is that clear? Okay, perfect, perfect. Let's have a look at this data and say daily the number of complaints which was received by a telecom department. That's they have been tracking the performance, the number of complaints, and they want to check the rate of complaints. Is it more than 20? Because people have been demanding for a new staff. So stats, basic statistics, one sample Poisson. It's count based. Sample count. Poisson is count. Pick the data, complaints. Hypothesis test. What is the target? 20. What is that we want to prove? That it is more than 20. The complaints we are getting is more than 20. If it is consistently and statistically proven that yes, the number of complaints are more than 20, then you will definitely get another additional resource to help you. Okay, perfect. Let's have a look at it. Sorry, it doesn't help. The rate of occurrence is 19.933, but the probability that the number of complaints can even go lowest up to 18.6. So you cannot say they are going to be always exceeding 20. So uh, you could sort of range here and there, but there's a probability that yes, the number of complaints can even go up to 18. So you can't say that you have like it's out of roof. No, it's more like a status quo situation. Sometimes you may be having more than 20, but it's not a regular feature, so you'll sort of balance out. So you can't demand for an additional resource right now based on the data. Sorry, we cannot give you additional resources. That's how it is. Count based testing. This is frequency based testing. So whenever we deal with numerical, like a count based stuff, it based on count, you do a one Poisson rate. When you talk about percentage based, like somebody has given you a targeting language of percentages, let's look at this one. It's like a say, okay, this is one is very, very common and people use this. A direct mail firm chooses 1,000 households at random to receive some advertisement from some new laundry detergent. So they've come up with some marketing plan. So some marketing plan is how they have decided that 1,000 families will receive this advertisement. Those 1,000 families who received the advertisement, 87 out of them purchased the detergent after getting that advertisement. The understood rate of success of the strategy, the marketing plan we had is that it gives you about 6.5% return on investment. So 6.5% success rate. We would like to check whether did this campaign do really well, and can we confidently say that we can continue with this particular plan because it's better. It is going to give us consistently 6.5 return rate, which is what we're probably looking for. Return on investment on the marketing plan. Let's check this out. We have no data. We have just summarized data. We can use it as it is also. So go to stat. We go to basic statistics here, and one proportion, one percentages, right? That's what we're talking about. Uh, we still don't have the data, so we can go to summarize data. We can select the summarize data. How many events are there? So 87 people purchased it out of 1,000. What is the desired proposed percentage? 6.5%. So 6.5 would be 0.065. This is 6.5%. I don't have a percentage sign here. We can't put it. We have to convert in numbers. So this is 6.5%. What is that we want to prove? It is greater than 6.5%. We want to prove that the minimum target that we had for to continue with this marketing plan going forward, to continue with this revised marketing strategy, is going to be if it delivers better than 6.5%, which is previously best proven strategy, probably the best return that we have been getting. Okay, let's see, did this strategy break the previous record? If it, then we will continue. Yes, absolutely. This confirms that yes, this strategy is definitely going to give you better than 6.5% return. The lowest you could expect from this strategy is 7.2%. The like for this sample, it's saying 8.5, 8 and 7, 8.7% return. But based on this percentage and based on the probability, we can confidently say, and how confident? 95% confident that we uh, we can see that yes, uh, this particular marketing plan will definitely give you more than 6.5% return. How much we can, the lowest we could expect is 7.2%, which is any given day more than your 6.5% requirement. So yes, this marketing plan definitely is a better plan than what you probably have been using. So that's his percentage based. So bottom line, these testing, every testing will have a target. There will be a why, and then you'll have a target to compare with. If you get to know that the process has achieved the target, great job. My job is done, and we can move ahead with the before and after validation. Before and after validation is even more simpler. Pretty much, it's just that what we end up repeating the same thing. So let's quickly have a look at this before and after validation. So before and after we do a paired t-test. So it says, as it says, we're comparing the average of old versus new. Average where we did a one sample t, we want to compare old versus new. Let's have a quick look at this Excel that we were talking about. Now I know whichever, like whatever test I would have might have performed, I know the target has been achieved. Whatever management wanted, we have been able to deliver that. Perfect. We have a proven strategy. Now it's just a matter about putting up the PowerPoint slides and sharing with the management to get their approval for full scale implementation. So the presentation work starts here. This data is already with us. So one slide goes for this. How did you know the process has significantly statistically improved? So the test results that we got will go on the first slide, followed by the before and after case study, which will include if you have gone for one sample, then you'll do a corresponding paired day. Depending on whatever you've done, you have a corresponding test. So how do we work in a paired T1? Let's quickly look at this one. Paired T test. This is some say heart rate, average heart rate before taking a medicine and after average heart rate after taking a medicine. So we want to check whether the medicine for heart rate, did it work or not. So null says there is no difference in your heart rate. Alternate says no, there is a significant difference and between the average heart rates before and after medicine, and we do a paired t test. So before and after, it's about paired t. Stats, basic statistics, and we have a paired t. Average of before and average of after. First sample, second sample. Null says no difference. Alternate says there is a significantly statistical difference. Okay, perfect. Well, null says there before the medicine, the average was 74.67, 667, and after the medicine is 72.233, whatever this. The difference is about 2.333. Based on the sample differences we are looking at, is that a large enough difference? Do you see? Is this difference a big difference between the two groups, old and new Y? Would you reckon this as a big difference, a statistically significant difference between old and new? Is it is it a different like a
No,
Yes, sorry, I'm
zero
on mute.
point 0.0. Yes.
this is less than 0.05? Alternate has been proven. Null says there is no difference. Alternate says no, there is a significant difference. And when we look at this, it does tell me there is a significant difference between null and alternate. And because this is the alternate, alternate means there is a significant difference between null and alternate. So yes, there is the drop and the difference in the old Y versus new Y is a significantly large difference. And definitely, yes, your medicine worked. So this test is used by all the pharmaceutical companies, the drug manufacturers, basically the psychiatrist before and after treatment, the weight loss program before and after, everyone, even the COVID vaccines before and after, the immunity before and after, everyone globally is doing paired t test right now. That's what is done for statistically proving that did you see an improvement? Yes. And is that improvement a stable improvement? Is that a significant improvement? There are a lot of companies who have tried for getting the approval for COVID vaccines. A lot of people have failed. Why? They couldn't clear the PAT test because the difference was there. But is that a significant difference? No. It could be probably the old immunity versus the new immunity could still show you some positive difference, but it's not a good enough difference for you to confidently say that did it did work and the difference in the immunity level was a great level reference. Sorry. So a lot of companies have failed, and that's why not everyone has gotten approval for getting this COVID vaccines in place. And that applies for everyone. Like the gym people, they show you before and after, stuff like that. Psychiatrists, food plans, and stuff like that. Everyone goes for this PAT test for regulatory aspect. So PAT test when you're comparing the averages. The logic remains the same, no, nothing changes. If you're doing before and after for median, then it becomes Man Whitney. We already know Man Whitney, we did it yesterday, but just like old and new, comparing the median. So stats, non-parametric, Man Whitney, old and new. Null says there is no difference in the median, alternate says there is a significant difference. And unfortunately, in this case, it doesn't support that. It says this the variance in that, like basically what we look at is it is not a conclusive evidence for you to say there is a big enough difference. It's null. It's null. So unfortunately, the medians, you can't say the median difference in the heart rate is significantly different. If in case you would have been comparing a median based test. Similarly, if you have variance based testing, if you have variance based testing, then you will be doing a two variance or test for equal variance, because we can do testing with either of them. A two variance or test for equal variance will do the same job. So you want to just test this for the test of equal variance, it will work fine. So because two test for equal variance does everything. So you have two data, separate data for every column, right? Yep. So put in your before, put in your after, job done. No, there is none. There's no difference between the old and new variance. The variance between them, the or the standard deviation between them, it is almost the same. Null 0.773. You do it with two variants, you will get same stuff here. Stats, basic statistics, and two variance test. Old and new, you have own column. Old data versus new data. That's it. Same step. Bonnet test 0.773. You get the same values. Bottom line, it's just about the concept of testing. That's what we got to keep in mind. Two Poisson, two
Sir,
proportion. Yes, yes, please.
why will I get to this stage here to and get a null if I'll be working on that in the target validation until I get an acceptable
Absolutely.
alternate?
You would know it. And that's why I say this is just about, this is when you know for sure it is, you not get null here. Absolutely not. So I'm like, this is, I'm just trying to kind of
Okay.
put, you would know that you would not get a null. And that's why you kind of showcasing before, you already know the target has been achieved. You know, there was a bad Y and you have improved Y. So technically this is just for to get the remaining things in place for you to seek an
Okay.
approval. So yes, you answer, the judgment is absolutely correct there. Okay, perfect. Have a look at this one, which is the next test in here, which is two Poisson rate and two proportion rate. So let's have a quick look at this one. Two Poisson and two proportion here. Two Poisson rate. So this is sort of some data for some branch, some postal office, two postal office, branch A and branch B. For 40 days consistently, the number of people who visited were tracked. Null says the uh, rate of people coming to branch A is same as rate of people coming to branch B. And trust, this test is used for in real estates when you have these shopping malls and the when we talk about the shopping malls, the price of the shops in these shopping malls is decided by the footfall in a mall, how many people turn up. That's what is used, this statistical testing is used there also to decide the pricing and to confirm that what is the footfall ratio, how many people turn up. So yes, that's where you compare this shopping mall supermarket with another supermarket. Is it better when you kind of trying to leverage your price, you want to sort of increase your prices and show that yes, you have a better footfall rate. You might want to do a survey and then have your prices inflated, and that's what people do. So say one shopping mall versus another. Null says both shopping malls or both supermarkets have almost same number of people visiting. Alternate says no, and one of them is a significantly difference. There is a definite difference between these shopping malls or supermarkets. Let's kind of check this out. Old versus new. So stats, basic statistics, we got two sample Poisson rate. Poisson is count. Own column, they're two separate columns, branch one, branch two, that's it. Null says there is no difference, alternate says there is a difference. The rate of occurrence is like 249 versus 257 based on the total count. For like it divides this to total sum divided by the count, gets the rate of occurrence. Is there a difference? And is the difference a large difference between them? uh, Pretty much based on this large difference, you can safely conclude that uh, the like it is there is a difference, and definitely branch B is more preferred and has a higher rate of a visit as compared to branch A. So count based testing, when you comparing, you would be doing this two Poisson rate. And on the same grounds, again, if you look at the other one, we have got two proportion test where you're comparing the percentages, like percentages of old and new. So, or two groups, two different groups, you're comparing them. So this is a like a very simple example. We can look at it, say some university financial aid office polled its undergraduate students to determine if male or female were more likely to get a summer employment. So during the job fair, job is like wherever the people recruiters do came, they came in for job interview. Uh, what happened is that 725 male candidates were picked up out of 802 male candidates who appeared for interview, versus 573 female candidates were picked up out of 712 who were interviewed. Based on this sample differences in terms of percentages, do you see a biasness of recruiters towards a particular gender, male or female? Let's find it out, the percentage of male versus percentage of female. Null says no, the recruiters were fair enough. They were not gender biased, and they had like an equal probability of picking from everyone. They had like they were like they sort of treated everyone's fair. Let's have a look at it. Two proportion, and we don't have the data. We have a summarized data here. Summarized data. Let's kind of put these values back here. 725 picked up out of 800 something, 802, and 573 females were picked up out of 712. That's it. Null says no difference in male versus female, and that's right. Unfortunately, the recruiters were gender biased, and definitely yes, they preferred more of male versus female. What you see, there's a percentage difference between male and female. And is that difference based on the samples that we have, sample difference, is that a large enough difference? Can you say there was, do you see the difference? And I hope this is not by chance. And yes, the p-value confirms no, this is not by chance, and the difference you're seeing is a real difference. And you'll always see the difference with this recruiter being there. So yes, you would not have this recruiter back again on your campus in that case. So are these differences real and not by chance? The answer is yes, it's not by chance. And the difference between old and new, or probably male female, there is a significantly statistically large difference. Now, just want to quickly check, are we okay with this so far?
Yes, it's clear.
Okay. Pretty much we have next things to be looked at, which is box plots. Say where we had this data of old and new comparison. I know we say whenever we did the old and new comparison, we would be more than happy to kind of we have the statistical test results. But other than the statistical test result, it needs to be we need to prove it through some sort of graphical plot. So yes, we will have the like, let me just get this one progressive. Let's kind of use this one progressive one. Let me copy paste this data. So wherever we did two some paired t-test or man-whitney test and stuff like that, we'll in the end have a box plot. So that test along with this box plot. So old, let me type in the old y and new y. So wherever we did a old and new comparison, the test we know, we will be doing a box plot. But this time box plot will be a little different from what we have been doing. Graph box plot, we have been doing with groups, but this time it's two y's, old y, new y. So multiple y's, which is what we will be using this one, y1, y2. Click on OK. Put in your old y, put in your new y. What was the target? The 13 minutes was the target given to you by the management. So 13 minutes goes to the reference line of 13 minutes. That's what we put in here. And if you want to make it like little clear, like you go to data view here, uh, and in that you can connect the median of the two box plots. So median connect line. It looks good. Nothing, no such real differences there. Uh, yeah, you can no. So this can be less than 30 samples also. This is fine. So this can be 30, more than 30. So because see, it's like you can work with the 20, 25 samples easily. Box plot ideally, let's a minimum of 20 samples are required. So you should be have quickly have a same data where you did the testing can be used for box plot. Same data. So whatever data you used and made a paired t-test, same data you'll be using for making a box plot. It clearly shows you the drop in the old versus new. The process has significantly dropped in terms of your turnaround time, and it has much it has shown you a considerable drop, which is what we wanted. Drop in the average handling time lesser the better. So that's what we have in terms of the time related factor. Say if we would have been looking at increasing the productivity, then we would have looked at things a little differently. uh, my data would have looked, the charts would have looked differently. They would have been trying to increase, so we would have done whatever test applicable. But let's see, if week one versus week two, we were trying to find out, we would have been doing this test graph, box plot, old one, new one. So we just put week one, week three. We put to go to the scale. The target was say 425 kilograms, and we connect the median connect line is already clicked. This is what will show you a steep increase in the production. So the statistical test along with the graphical test will help us validate, yes, did your process improved or not? Yes, that's how it is. Yes, my process has significantly statistically improved. Uh, that's about the test of like testing the statistical like graphical plot. The control charts before and after, we haven't studied control charts. We'll just try to see where to find that, but the interpretation will sort of mark it for tomorrow when we do complete the control phase. But let's see what how to get that control charts. Not for this one, like we don't have it here, the before and after one. Let me just, we'll be rather using the system in this case. Before and after control charts. Before and after control charts, we select the old, this is the first one we have to select, before and after IMR chart. Tomorrow in which we will understand these charts. IMR chart, the old column, the Y and X, no, we have two separate columns of all Y data, no. Here they are in two separate columns, Y in two columns, old Y, new Y, before Y, new, after Y, old Y, new Y, Y equal 1, week 3, so old and new. That's it. Just click on it. It'll prepare the reports. It'll have your control charts available. This is the old Y control chart, the new Y control chart. The interpretation we got to park it for tomorrow when we complete the control phase tomorrow. But pretty much that's how it looks like when you kind of look into the control charts. Control
How
charts
do we
and
export these charts to
you,
another document?
you just right click and it'll be fine. So just copy the graph, paste it
Okay.
wherever you want. So
Okay.
and it's completely editable. So when you're done with, you don't want like the color, you want to change anything, do your changes with the wherever you are, and then you can sort of, then done with it, just take it, transfer it wherever. If you're working on mintab 19, which even gives you a drop down box here to kind of save as an image and stuff like that. So if you generally, if you're working on minitab 19, I'm working with the older version. On minitab 19, you get generally this chart will not pop up, it will be there in the screen itself, and you just get a drop down there. It gives you option to save the graph, open a PowerPoint, open a Word document, and then paste it there, save as an image, do whatever you want. So practically it's a very very handy stuff that you can work on. Having said that, yes, this is control charts before and after, and then you have before and after sigma levels. So that is what we will also be submitting as before and after sigma levels. If your data is normal, then you can follow a simple route, which is you can use the assistant option, before and after capability. This you can use before and after capability directly if your data is normal. This is not meant for non-normal data, so do not use it for non-normal. For non-normal, you have to follow the other route. Let me first go with a normal one. Data is continuous, the data is normal. We click on this. What is your old Y baseline process data? Where did you start from? Okay, this is where I started from week one. What is your subgroup size? Single subgroup, single column. Which one is your improved process data, new process data, which is the new process data is week three. What is the subgroup size? Single columns. That's what we have. What is the specification limit? Client wanted a minimum of 425 kilograms. Anything less than 425 would have been considered as a defect. Okay, that's it. Got your sigma levels checked. Comparison of old and new sigma level. This is where we were earlier. 425 was here. Shifted significantly. Yeah, we still have some production below 425, but we have achieved a significant improvement from here till here. If we look at this, it says 77% reduction in defect. Earlier, your 100% process was defective. Now it's down to only 22% defect in your process. It's down by 77%. If you look at this same, the change old sigma, new sigma, change in the sigma, that's what it tells you. Again, if you look at other stuff, it gives you control charts on its own, old and new control charts. You don't have to do it separately. It comes on its own. Old chart, new chart, the old sigma level, old normality test, new normality test. It looks at everything and gives you a complete performance report about your process. The CPK, the PPK that we have, I'm sure we recall that. CPK, PPK, the long-term sigma percentage, the old sigma, the new sigma. You have to keep remember this in mind. This is not talking about current sigma. You have to always add 1.5 to the set bench to get your current sigma. So current sigma, you have to convert it by adding 1.5. No software will give you uh, 1.5 addition. You have to do that manually. So when you published this, again, let me sort of quickly redo this one. So when we did this activity, you could make those corrections and mention it here. Should you want to make some comments here? Yeah, you can add in here. Since the long-term sigma is so and so, so your current sigma is so and so. Make your comments there, and then you can click. It will come here as it says. It's a personalized report. A lot of things been explained already, so you can use this. But keep this in mind. This is only applicable for normal data. For non-normal data, you cannot follow this process. Remember, for non-normal data, you have to find the distribution first. Distribution first. So individual distribution identification has to be done. You have to follow this path for capability analysis non-normal. That was we did. Now we are talking about multiple non-normal. So you can do this before and after for normal from here also, and before and after for normal or non-normal here. But if both the data, old and new, follow the same distribution, then the job is easy. Otherwise, you have to kind of do it separately because it doesn't give you two separate options for distribution. So if both week one and week three, you have to do individual distribution identification for both of them. If both follow the same distribution, then you can perform a comparison of sigma levels on the same. Assume that both have same viable distribution, and there is target of say 425. If I'm using this, so both week one, week two, they have a viable distribution, and we are working with a target of 425. That's what I need to do. It will publish the sigma levels for me. Let's have a look at this. So this is week one, this is week two, see in the same chart. But for non-normal data, if your data is non-normal, that's when you will be using this one. But otherwise, if it's separate, then you have to go and find out sigma levels separately for this and sigma levels separately for this if the data distribution differs, because your old data can be have a different non-normal shape and your new non-normal data can have a different non-normal shape. It's quite possible. So if it is same for both of them, then you can straight away go and do it. Otherwise, you have to go parallelly one by one with non-normal for both of them and then put it on your graphs and charts. That's how we put it. Is this okay with everyone? Like the basically this is all what you're going to be putting on the slides just to seek an approval. Is this okay?
Yes, it's clear.
And pretty much the last one, which is sort of not applicable like for us, but we should know it. It is the cost benefit analysis. The cost benefit analysis is just about seeking an approval from the management to go for full scale implementation. You're given them the statistical validation You show them the results, the before and after, the sigma level stuff, everything. In the end, everything matters is money. Money is what matters. So yeah, your it's not your responsibility. The finance guy would definitely be doing this, but we should know what does it mean, and it shouldn't sound like an alien term to me. So basic terms: one is net present value, which is NPV. Internal rate of return is IRR, and payback period is PBP. Uh, the accurate ones are would be the first two ones. This is not accurate, but very much used in traditional layman language. People use payback period also, but accurate ones are the first two ones which we can use and which are used by the industry where people are, I would say, follow a rational approach. So let's take a simple example to understand this. These are very, very simple. You don't have to do any separate calculation for this. It gets easily worked out. Let's take a simple example. That solution that I'm talking about, it is going to cost about $1 million or 1 million, whatever currency. And say I'm buying a machinery, some sort of machinery that I'm sort of proposing that we should go and purchase this machinery as a part of my solution. And if we do this, there will be benefits and we'll be able to generate a lot of revenue and profits and stuff like that. The question is, can we or should we go for this investment? Does it make sense to make this investment today? So that's a question how we would be tackling with this net present value and IRR. So assume this is $1 million or whatever, some currency we are looking at. And based on my understanding and experience, the subject matter experts, the process experts, they have sort of given a projection that after after implementing this solution, obviously we'll be getting more revenue, more profit margin. So this is your net profit projection year on year. So based on the experience, they're saying like we will be able to recover about 250,000 in the end of first year, by the 250,000 other at the end of second year, third year, fourth year, and so on and so forth. So this is like say another 250,000, and then believe that we will be able to
Hello, Shashi.
Yeah, I think we lost him.
Hello. Sorry, I got disconnected. I guess there was some network fluctuation. I hope I'm audible.
Yes, sir.
Okay,
Yes.
I'm so sorry about that. So, uh, I guess uh, I'm not sure whether were you able to hear me till what point, but I'll just quickly recap. So we were talking about this net present value, where we were talking like we say if we have some projections which we have for next say 5 years, and we believe that we will be able to kind of get certain returns. These are post the cost deduction has already been done. So if we were to calculate the net present value, the formula is pretty simple. See, just try and first of all relate with it. This is what we talk about, like $1 million or 1 million rupee or whatever currency we talked about, and this is what we will be able to recover. If I just look at this recovery or the return that I'm looking at, so this is more like we add up all of these, it is going to be better. It's a better proposition because I'm making about 1.15 million. That's about like much better investment return when I look at if I invest 10,000 like a million rupee or dollar, and I get a good amount of return like a post 5 years. But in the language of net present value, probably it has a different meaning altogether. Why? Because the investment that I'm doing, which is $1 million, say it's worth 1 million as of today. But this 250,000 that I'm talking about, which I will get at the end of first year, will not be worth 250 at the end of first year. The value of the money would depreciate. The whatever I could get today for 1 million, it is worth 1 million. But this 250 is in future. This money will not be worth 250. This money that I'm getting after second year, it will not be worth 250,000. This early money which I'm getting at the end of the third year will not be worth 250. So practically, when I look at it, it's a profitable destination. Yeah, when I look at the absolute number, yes, but will the worth of the money be still the same? No. Over a period of time, because of inflation and everything, the value of money will get depreciated. So what I need to do is find out what is the future values money of this 250,000 in current scenario. Whatever I'm making, like in the first year, what's the worth of it in today's scenario? What's the worth of this 250 at the end of 2 year in current scenario? And bring in every future money in current scenario, and then see, is it more than 1 million or is it less than 1 million? If it's less than 1 million, then it's no point in doing that investment. But if it is more than 1 million, then definitely it's a good option. So if I go with a net present value logic, NPV is net present value. I open up the bracket. It is asking me for a rate. Rate is used generally as for a fixed deposit rate. This is something called, which is a dead rate, free rate, like the risk-free rate. You will any which ways earn if you choose not to invest in my project, fine. But if you choose to put it somewhere where you will get 100% guaranteed return, and generally it's like a fixed deposit. Whatever is a fixed deposit rate at that point in time will be used here. Say it's like in India, we talk about like it's currently say 6%. So I put in 6%. If I choose not to invest, I will obviously be making 6% return over a period of time. That's my benefit if I go with this, compared with starting from here, including the negative sign, till the end of fifth year. That's what I have to do. If the thumb rule is, if this comes negative, don't invest. It's bad. Save the money, put it in the FD. If this comes positive, then don't put it in FD, invest your money. This is a very, very bad proposition. Don't ever even think about investing this money in this particular plan, because it is, if you currently calculate the future money, bring future money in current scenario, you will be losing 22,525 rupees or whatever this dollars. If it's 1 million, then you will be falling short of this much in current. If you bring every future money in current scenario, you will be falling short of this money, which is bad. Assume that this machinery that I was talking about, we end up selling this machine after end of years. We probably scrap it off at the end of, say, whatever period. We junk it and we scrap off this machine because it starts giving wear and tear, some damage, some issues. So we junk this machine for say 300,000. It's an old machine, pretty much giving issues. We have already reaped the benefits from it, but we still sell this machine in a scrap over, and this is what we get. So now, because that is also capital return that I will be getting,
So I'll still be going with the same logic, but here I will be extending this to next column also. Now let's see. Yes, that's a profitable business. And yes, if that's going to happen, go for the investment. The thumb rule is if the NPV is negative, do not invest in the project. If the NPV is positive, yes, it's worth investing in that project. All banks, all financial institutions will look for NPV as the criteria. That's the criteria they use for making the future plans. You invest this much money, keep investing money month, year and year. After 25 years, we'll give you this much of money. So if you really want to understand, the money they promise that they will give you after 25 years or 20 years actually will not be worth that money. So if you want to convert that future money in current scenario, then technically you will see that they are always on the winning end, you are on the losing end. So net present value is what they use for calculation to make those plans and projections for you. So net present value is very simple stuff. Similar logic on net present value is IRR. IRR is nothing but internal rate of return. This language is used by generally the people who are investors. I'm like people are talking about startups and all that, angel investors, VC, and all that people. So these guys just ask you a simple word: what will be the return on investment? How much money will I be able to make? What's ROI? So how do I get it? Take it from the negative, the investment, till the recovery. And these guys generally would say that they would have their preferred percentage. If you are submitting some ideas or startup projects, give me, I will only look into that project which gives me minimum 15% return. I need 15% return. Anyone who can give me, I will be able to evaluate that project. So these guys have a clear line of sight. Money is the only definition they understand, and they'll only be asking for a clear cut percentage. If you can qualify, great. If it's not, then it's not good. IRR 12%. If I need 15%, this project will not work out in the eyes of investor. If the investor is looking for minimum 12% return, sorry, this is giving you only 12%. So that's not a good enough project in the eyes of that investor. Probably the investor is looking at 10%, then it's good. So IRR is just simply select all the starting from negative till all the returns, you get your IRR. And these are the correct version because everything is being future factored in for future to current kind of ratio is taken care of. This payback period is an absolute raw way of calculating and doesn't look into the future money in current scenario. It's absolutely raw. If I look at it, I invested $1 million. Day zero, this was my entire loss. I'm saying at the end of first year I'll recover about $250,000. The money which I had to recover more will be 7.5 million, $7,500. At the end of the second year, I would again sort of recover another 250, so I'll be left with another 500,000. If I recover another 250, I'll be left with another 250,000. At the end of fourth year, I'll sort of recover 200,000 more. I will left with 50,000 to recover. Only in the fifth year is when sort of my money would have already come back and I would have made profit. I would have made profit in the fifth year. Now, what is the basic logic? Payback period. When would I get my money back? And after that period, my profits will start. That's what it means. It doesn't look at it just looks at absolute value. Now, how do we calculate it? The year when you're getting profitable, just go before that. So if I'm getting profitable in the fifth year, just go before that. So fourth year is when I'm getting profit. So there's no rocket science. It's a very, very layman version. Fourth year is when I'm getting profitable. 4 year plus, open up the bracket. How much more you need to recover? 50,000 more we have to recover. So because there's a negative sign, for understanding, say we have kept negative there. So I will put a negative to cancel this negative. So 4 years, I would have recovered all my money. The only thing which I have to recover is this 50,000. So I select this 50,000. This is more I have to recover. The rest, everything I have recovered in 4 year. 50,000 more needs to be recovered. And my next year projection is 200,000. So how long will it take for me to recover this 200,000 from the next year? Logically, there's no other meaning to it. 4.25. This okay. This is probably I have made a blunder somewhere. 4 plus. Okay, I must have made some blunder.
4 plus k minus 50,000 by 200,000, I guess. Okay, probably let me do it somewhere else. Probably this has some percentage value feed in it already. 4 is when I recover everything, plus what I need to recover is minus this divided by this. Yeah, 4.25. So I need 4.25 years to recover my investment. That's what, beyond 4.25 is when my profits will start. So payback period, the money will be returned in 4.25 years. That's what I have. So honestly, I can see we don't end up doing this, but we should be able to. We should know what it means when people are sort of sharing this stuff and all that. We should know at least what these terms mean. Now, quickly checking with you all. Are we okay? Sort of thing. This is sort of we conclude the improve phase. Yes, so we'll be left with the control part, which we'll be looking in tomorrow. But yes, is it okay? Everyone is okay with this?
Yes.
Yes.
All right. So let me. So I'll put up all these files. Give me like some time. Like let me just clean. There are a lot of multiple files here and there. So I'll sort of clean up and make a proper file and put it in the Google Drive. So give me like half an hour, like probably by time until morning, and I will sort of kind of clean up and put a proper file so that you don't have to kind of scroll through multiple pages. All the data files, what you need to do for these tests. So that will be one single file that you can access and you can practice it later on. All right, so let's then catch up tomorrow, and let's start with a. So tomorrow we'll be kind of working on control phase, and we'll complete the lean part of it. The last day we'll be parking for design of experiment, and we'll discuss about the project, the simulation project part of it. So that's how we are planned for next couple of days.
Thank you.
All right, thank you.
Okay, thank you.
Take care.
Thank
Thanks.
you, sir.
Thanks. Bye bye. Thanks. Take care.
Bye.
Bye bye.